Good day everyone! In this video, I will be discussing chapter 36, which focuses on diffraction, one of the most important phenomena that demonstrates the wave nature of light. So many of us think of light as something that travels in straight lines. In fact, this idea forms the basis of geometric optics. However, when light encounters obstacles or passes through a very narrow openings, it behaves in a surprising way. Instead of moving in only straight paths, light bends and spreads into regions that should have been dark. This phenomenon is the study of diffraction has greatly influenced modern science and technology. It helps us understand how telescopes form images, how CDs and DVDs store information, how scientists determine the structure of crystals, and even how holograms are created. In this presentation, we will explore the principles behind diffraction, examine different diffraction patterns, learn about diffraction gratings and X-rays, and understand diffraction limits and performance of optical instruments. Before we begin, let us look at the learning objectives of this chapter. By the end of this lesson, we should be able to understand how apertures and sharp edges affect light, analyze diffraction through single slit, calculate light intensity in diffraction patterns, investigate the behavior of light passing through multiple slits, explain how diffraction grating separates wavelengths, understand how X-ray diffraction reveals crystal structures, describe how diffraction limits the resolution of telescopes, and explain the basic principles of holography. So these concepts will help us appreciate the practical applications of wave optics in modern science and engineering. Let us begin with two interesting questions. First, how can we distinguish between a CD, a DVD, and a Blu-ray disc using light? Second, why does a razor blade create alternating bright and dark bands instead of a perfectly sharp shadow? The answer to both questions lies in diffraction. Diffraction occurs because light behaves as a wave. When waves encounter obstacles or narrow openings, they spread out and interfere with one another. This chapter continues our study of the wave nature of light. Previously, we discussed about interference. So diffraction is closely related because it also involves the superposition of waves. By understanding diffraction, we can explain many optical phenomena that cannot be explained by ray optics. According to geometric optics, an object placed in front of a light source should cast a sharp shadow. However, real observation shows something different. Instead of producing perfectly sharp boundaries between light and shadow, the edges appear blurred. Bright and dark bands may also appear near the edges. This effect is called diffraction. Diffraction is the bending and spreading of waves around obstacles and through openings. The effect becomes most noticeable when the size of the opening or obstacle is comparable to the wavelength of light. Diffraction is not unique to light. Sound waves, water waves, and even matter waves exhibit diffraction. The existence of diffraction provides strong evidence that light behaves as a wave. To understand diffraction, we must use Huygens principle. According to this principle, every point on a wavefront acts as a source of tiny secondary wavelets. As these wavelets spread out, they combine to form the next wavefront. Huygens principle explains why waves can bend around obstacles. There are two major types of diffraction. First, we have the Fresnel diffraction, also called near-field diffraction. This occurs when the source, obstacles, and screen are relatively close together. The resulting pattern is also complex. Another type of diffraction is the Fraunhofer diffraction, also called the far-field diffraction. This occurs when the source and screen are far from the obstacle. The resulting pattern is simpler and easier to analyze mathematically. Consider a beam of light passing through a narrow slit. Geometric optics predicts that light should pass straight through and create a bright region with sharp edges. However, actual observation shows that There are broad patterns consisting of a bright central region surrounded by alternating dark and bright fringes. This is called a single-slit diffraction pattern. One of the important observations is that the narrower the slit, the wider the diffraction pattern. This may seem surprising at first. So when the slit becomes narrower, the spreading of waves become greater. This relationship is fundamental to diffraction. This slide compares Fresnel and Fraunhofer diffraction. In Fresnel diffraction, the wavefront reaching the obstacle is curved because the source is relatively close. The diffraction pattern changes depending on the distance between the screen and the obstacle. In Fraunhofer diffraction, the wavefront is essentially flat because the light source is very far away. The diffraction pattern remains stable and can be analyzed using simple mathematical equations. Because of this simplicity, Fraunhofer diffraction is widely used in optical experiments and engineering applications. To determine where dark fringes occur, we examine the interference between wavelets emerging from different parts of the slit. At certain angles, wavelets from one part of the slit cancel wavelets from another part. This destructive interference creates dark regions called minima. The condition for minima in a single slit is shown in this slide, wherein A is the slit width, theta is the diffraction angle, lambda is the wavelength, and m is a non-zero integer. Whenever this condition is satisfied, a dark fringe appears. This equation allows us to predict the position of minima in the diffraction pattern. In this example, 633 nanometer light passes through a narrow slit. The diffraction pattern is observed on a screen located 6 meters away. The distance between the central maximum and the first minimum is measured. Using the diffraction equation, we can calculate the width of the slit. This example demonstrates an important application of diffraction, measuring extremely small dimensions. Scientists and engineers often use diffraction techniques to determine the size of microscopic structures. The diffraction pattern is not equally bright everywhere. The central maximum is the brightest region. The brightness gradually decreases as we move away from the center. This variation occurs because wavelets combine differently at different angles. Some positions produce strong constructive interference, while others produce partial cancellation. The result is a characteristic intensity distribution consisting of bright and dark regions. Understanding this distribution is important in optical design and image formation. This slide illustrates how the diffraction patterns develop. Each point along the slit contributes an electric field vector. These vectors combine to form a resultant vector. The size of the resultant vector determines the brightness at a particular location. When vectors add together constructively, the intensity becomes large. When vectors partially or completely cancel each other, the intensity decreases. This vector approach provides a visual understanding of how diffraction patterns emerge. The intensity of a single slit diffraction pattern can be calculated mathematically. The result is known as the sink square distribution. The intensity depends on the phase difference between waves coming from different parts of the slit. This equation predicts the exact brightness at any angle. It explains why the central maximum is brightest and why successive maxima becomes progressively weaker. The mathematical model agrees very closely with experimental observations. The intensity graph shows a dominant central maximum. Notice that the central peak is much wider and brighter than the others. The secondary maxima becomes weaker as the angle increases. An interesting feature is that the maxima do not occur exactly halfway between the minima. This behavior differs from ordinary two-slit interference. So the intensity distribution is a unique characteristic of single-slit diffraction. The width of the diffraction pattern depends on the ratio of slit width to wavelength. A wider slit produces a narrower diffraction pattern, while a narrower slit produces a wider diffraction pattern. Similarly, longer wavelengths create a broader diffraction patterns. This relationship explains why radio waves can bend around buildings more easily than visible light. It also explains why diffraction becomes important in optical systems containing very small apertures. Previously, we studied two-slit interference, assuming infinitely narrow slits. In reality, every slit has a finite width. As a result, the observed pattern is a combination of interference from the two slits and the diffraction from each individual slit. The interference fringes appear inside a broader diffraction envelope. This combination creates the complex patterns commonly observed in laboratory experiments. Now let us increase the number of slits. As more slits are added, bright maxima become sharper, dark regions become darker, and the patterns become more distinct. A lens is often used to project the Fraunhofer diffraction pattern onto a nearby screen. This allows detailed observation without requiring extremely large distances. Now let us increase the number of slits. As more slits are added, these slides compares patterns produced by 2, 8, and 16 slits. Notice that increasing the number of slits causes the bright peaks to become more narrower and more intense. This improvement is extremely useful because it allows different wavelengths to be separated more clearly. When white light passes through many closely spaced slits, each wavelength forms maxima at slightly different angles. As a result, the light spreads into a spectrum. This principle forms the basis of diffraction gratings. A diffraction grating contains thousands of equally spaced slits. The condition for bright maxima is shown in the slide, where D is the slit spacing, M is the order number, and lambda is the wavelength, wherein the different wavelengths appear at different angles. Because of this, diffraction gratings are excellent tools for separating light into component colors. A diffraction grating contains a spectrograph uses a diffraction grating to analyze light. When sunlight enters a spectrograph, it is separated into a spectrum. Dark lines known as absorption lines appear within the spectrum. These lines reveal the chemical composition of stars and galaxies. Astronomers use spectrographs to determine the temperature, chemical composition, motion, and the magnetic fields of distant celestial objects. This diagram shows the major components of a diffraction grating spectrograph. Light enters through a slit, passes through an optical components, and reaches the diffraction grating. The grating separates the wavelengths according to angle, and a detector records the resulting spectrum. Modern spectrographs are among the most important tools in astronomy and analytical chemistry. This diagram shows the major components. Visible light cannot reveal atomic structures because its wavelength is too large. However, X-rays have wavelengths comparable to atomic spacing. When X-rays pass through crystals, they undergo diffraction. The crystal acts as a three-dimensional diffraction grating. By studying diffraction patterns, scientists can determine the atomic arrangements inside the materials. This technique revolutionized modern science. The condition for constructive interference in X-ray diffraction is called the Bragg's law. This equation relates to crystal spacing, diffraction angle, and X-ray wavelength. Using Bragg's law, scientists can determine the internal structures of crystals. This method played an important role in discovering the structure of DNA. The condition for constructive interference in X-ray diffraction. Not all openings are slits. Many optical systems use circular apertures. A circular opening produces a diffraction pattern called an airy pattern. The bright central region is called the airy disk. So the first dark rings occurs at sin theta is equals to 122 lambda over d, where d is the aperture or the diameter. This relationship is important for understanding image diffraction affects every optical instrument. Even a perfect lens cannot focus light into a single point. Instead, diffraction produces an airy disk. When two objects are very close together, the airy disk overlap. If the overlap becomes too large, the objects cannot be distinguished. This limitation is called the diffraction. Large telescopes have larger apertures. According to the diffraction theory, increasing aperture size reduces the size of the airy disk. As a result, resolution improves. This is why modern observatories build extremely large telescopes. Large radio telescopes such as the Very Large Array can produce remarkably sharp images of distant astronomy. Holography is a technique for creating three-dimensional images. A laser beam is divided into two parts. One beam illuminates the object, and the other serves as a reference beam. The two beams interfere and produce a complex pattern that records both intensity and phase information. Unlike ordinary photographs, holograms preserves depth information. Holography is a technique when laser light interacts with an object. The reflected waves combine with the reference beam. The resulting interference pattern is recorded on a photographic medium. When illuminated correctly, the recorded pattern reconstructs the original wavefronts. The observer sees a realistic three-dimensional image. This process relies heavily on interference and, when laser light interacts with an object, the images shown demonstrate how a hologram changes perspective when viewed from different angles. Just like viewing a real object, moving your head changes what you see. This depth perception is what makes holograms unique. Today, holography is used in security labels, credit cards, data storage, medical imaging, and scientific visualization. The images shown demonstrate. To summarize, diffraction is the bending and spreading of waves. Huygens' principle explains diffraction. Single-slit diffraction produces characteristic bright and dark fringes. Diffraction gratings separate wavelengths into spectra. X-ray diffraction reveals crystal structures. Diffraction limits the resolution of optical instruments, and larger aperture provides better resolution. Also, holography uses diffraction interference to create three-dimensional images. And these concepts provide powerful evidence that light behaves as a wave. That concludes our discussion on diffraction. Understanding diffraction helps us explain phenomena ranging from shadows and spectra to crystal structures and holograms. It is one of the most important topics in wave optics because it connects with fundamental physics with practical technologies used in astronomy, medicine, communications, and materials science. Thank you for listening, and I hope this presentation has helped deepen your understanding of the fascinating wave behavior of light.